Welcome to this explainer. Today, we're cracking open the universe's ultimate accounting rulebook to see exactly how energy gets managed on a macroscopic scale. We are diving headfirst into the fascinating world of thermodynamics. You know, those fundamental rules dictating how energy converts from one form to another?
So what do a car engine, a lithium battery, and your own body actually have in common? You might instantly think of mechanics or chemistry, maybe biology. But at their core, they're all completely governed by thermodynamics. From burning rocket fuel to the biological processes keeping us alive, this discipline proves that every single action in our universe is fundamentally just an energy transaction. It helps us understand exactly how much energy is in play, whether a process will even happen at all, and how far it'll go before finally settling into equilibrium.
To properly audit this universal system, we split today's agenda into 5 parts. 1. Setting the universal stage. 2. Energy, work, and heat. 3. The first law and enthalpy. 4. Measuring energy in action. And 5. Why thermodynamics runs everything. Let's get right into it.
Section 1. Setting the universal stage. Okay, let's establish exactly where these cosmic energy transactions are taking place.
In thermodynamics, we take a highly complex reality and simplify it by splitting the entire universe into just 2 parts. First, we have the system, which is just the specific part of the universe we happen to be studying right now, like a chemical reaction bubbling away inside a beaker. Then we have the surroundings, which is literally everything else outside that system: the room, the planet, the whole shebang. So, the universe is simply the system plus its surroundings.
Now, our metaphorical bank, the system, can interact with the outside world in 3 distinct ways. An open system freely exchanges both energy and matter with its surroundings. Think of an open beaker. Heat easily escapes and liquid can spill right out. A closed system, like a tightly sealed container, locks the matter in but still allows energy to flow back and forth. And finally, an isolated system, kind of like a really good thermos flask, allows absolutely zero exchange of either energy or matter. It is completely cut off.
We define a system's current condition using what we call state variables: pressure, volume, temperature, and amount. The truly beautiful thing about state variables is that they only care about the system's current state. They completely ignore how it actually got there. It doesn't matter if your system was heated in a flash or slowly simmered over a week. If the temperature right now is 298 Kelvin, well, that is its state variable. The past history simply doesn't matter.
When we look at these properties, we absolutely have to distinguish between 2 categories: extensive and intensive. Extensive properties scale up when you add more stuff. If you double the liquid in a beaker, the mass, the volume, and the total energy all double. Makes sense, right? But intensive properties are built-in characteristics that stay exactly the same, totally regardless of the amount. Whether you have a tiny microscopic drop of water or a giant swimming pool full of it, the density and the temperature of that water remain absolutely identical.
Moving on to Section 2, energy, work, and heat. Let's look at the actual universal currency used to fund all these transactions.
Think of internal energy, which we denote with the letter U, as the total bank balance of our system. It encompasses literally all the kinetic, potential, and chemical energy hiding inside. Internal energy is a state function that only changes when a transaction goes down. Specifically, when heat is added or removed, work is done, or matter physically moves in or out of the system.
So, the absolutely crucial point here is that energy is deposited or spent through 2 primary currencies: heat and work. Heat, represented by Q, is energy transferred purely because of a temperature difference. If the system absorbs heat, it's a positive gain. If it releases heat, it's a negative loss. Work, on the other hand, represented by W, happens when a force causes displacement. Specifically, pressure-volume work in the systems we're talking about. When a system gets compressed, work is done on it, making it positive. But when it expands, it's doing work on the surroundings, which makes it a negative expenditure.
These energy transactions generally happen in 2 main ways. First, you have a reversible process. This is an idealized, theoretical scenario that happens infinitely slowly, staying perfectly balanced in equilibrium the entire time. Because it's so perfectly balanced, you could, theoretically at least, reverse it without losing a single drop of energy. But an irreversible process, that's what actually happens in the real world. Think about scrambling an egg or shattering a glass. It happens rapidly, it's totally out of equilibrium, and there is absolutely no way you can perfectly undo it.
Section 3. The first law and enthalpy.
Now we've reached the absolute golden rules of our universal accounting system.
This brings us to the first law of thermodynamics, the ultimate unbreakable law of conservation. It simply states that energy cannot be created or destroyed, only converted from one form to another. That famous equation, delta U equals Q plus W, shows us that any change in our system's internal energy balance is perfectly, mathematically accounted for by the exact sum of the heat transferred and the work done. Literally, every single unit is accounted for. There are no missing pennies in this ledger.
Now, tracking both heat and work in an open environment can be a real headache. Since most real-world chemistry happens in open beakers at a constant atmospheric pressure, scientists use a special, highly useful ledger called enthalpy, denoted by H. Enthalpy is just the system's internal energy plus the product of its pressure and volume. It specifically allows us to track heat transactions seamlessly when the pressure stays exactly the same.
Looking at changes in enthalpy gives us two very distinct types of chemical reactions. If you keep in mind that heat is our currency, an exothermic reaction is basically an expense. It's paying heat out to the surroundings, meaning its delta H is negative. An endothermic reaction, though, is a deposit. It's taking heat in, which gives it a positive delta H.
The speed at which a system's temperature actually changes during all these heat transfers depends entirely on its heat capacity, represented by the letter C. This measures exactly how much heat currency is required to raise the system's temperature. It's a pretty straightforward relationship. The larger the heat capacity, the more heat you have to pump in, and the slower the temperature rises. It's exactly why a metal pan heats up instantly on your stove, but the water inside it takes ages to actually start boiling.
All right, Section 4. Measuring energy in action. Let's look at how we actually audit these invisible transactions in the real world using a clever technique called calorimetry.
We typically measure heat changes using two main tools. And hey, don't let the name scare you. A bomb calorimeter is definitely not a weapon. It's just a heavily reinforced, completely sealed container designed to keep volume absolutely constant. Because the volume can't change, there's zero pressure volume work being done. That allows us to measure the direct change in internal energy, delta U. By contrast, a simple calorimeter operates at a constant, everyday atmospheric pressure. That makes it the absolute perfect tool to directly measure changes in enthalpy, or delta H.
To handle all sorts of different chemical processes, we have to use several specialized ledgers. We track the overall heat with enthalpy of reaction, or measure the precise energy required to form a compound with enthalpy of formation. We even have specialized tracking for phase transitions, like melting or vaporizing, combustions for when substances burn completely, and bond enthalpies to measure the raw shear energy locking atoms together in a solid.
And tracking all these different enthalpies brings us to an incredibly beautiful shortcut, Hess's Law. Hess's Law proves that because enthalpy is a state function, remember, meaning our accounting system only cares about the initial and final states, the actual path taken doesn't matter at all. We can safely audit super complex, difficult-to-measure chemical reactions simply by breaking them down and adding up the enthalpy changes of the smaller, easily measurable steps along the way. The total change always equals the sum of its parts.
Finally, Section 5. Why thermodynamics runs everything. Let's tie all these formulas back to why this is the absolute, undisputed backbone of modern science.
Thermodynamics isn't just abstract textbook math. Mastering these strict rules allows us to literally predict the future of chemical reactions. It's the exact framework engineers use to design hyper-efficient engines and develop incredibly powerful new industrial fuels. It even forms the very foundation of biology, helping us fundamentally understand how our own bodies process food and convert it into the kinetic motion of, well, a heartbeat.
We've seen today how the universe perfectly balances its books, never losing a single drop of energy, but endlessly transforming it from heat to work to chemical potential and right back again. Since every single breath you take and every move you make is a perfectly balanced thermodynamic transaction, I leave you to wonder, how will you spend your energy budget today? Thanks for exploring the rulebook with me.